everyone. Welcome to the mind map of this chapter. Actually, it is made up of two chapters, which is one of them is SHM, simple harmonic motion, and the and the other one is wave, which can be seen as the extension of SHM. Now, first of all, we will talk about oscillatory motion. What is an oscillatory motion? Oscillatory motion. Motion in which a particle moves in certain direction and then comes back and then it comes back. It just moves in this direction, in this way, and that is called oscillation. The mean position is fixed. It is always oscillating about a fixed mean position. This sort of general oscillatory motion is there. Now, a special type of oscillatory motion is called simple harmonic motion. Harmonic motion, in which, let's say, this is the mean position. The particle starts from here. Let's say it is here after some time, covering some distance x, then the force that is being exerted on the body will be restoring in nature, because every particle would like to return to its original position in this type of motion. So the force will be in this direction, and the force is actually directly proportional to the distance x. When this condition is satisfied, that the restoring force on that particle is always directly proportional to the distance which it has covered towards the opposite direction, it means towards, always towards the mean position, that would be called a simple harmonic motion. That is the basic definition, that force is directly proportional to x, or actually minus x. Why? Because force will be always in the negative direction of x. If this is the mean position, the particle has moved right in the right direction, then force is going to be exerted in the left direction, so that uh, इट कम्स बैक टू इट्स ओरिजिनल पोजीशन, ये वापस आ जाए अपने ओरिजिनल पोजीशन पे. उसके लिए हम अगर कोई पार्टिकल आगे जा रहा है तो उसको वापस आने के लिए पीछे फोर्स लगाना पड़ेगा ना. दैट इज द मीनिंग ऑफ दैट. सो इफ यू सॉल्व फॉर इट, then converting proportionality into equality, that becomes f is equal to some constant into x. Since minus was there, I have just put it there. Now this is the basic definition of SHM. Whenever you have to apply the properties of SHM, you may take the help of this equation at the fundamental level. Everything in the simple harmonic motion is derived from this equation, further derivation from it. For example, if this is force, then I can write it as mass into acceleration is equal to minus kx. Now here, mass into acceleration, what's the definition of acceleration? Acceleration is equal to, there are two actually expressions for that, dv by dt, and another could be a is equal to v dv by dx, right? So if you replace dv by dt, it becomes a very simple thing. dv by dt, actually it would be much difficult to solve. Then I would replace it with v dv by dx. Now it's much easier. Now m is a constant multiplied by v dv is equal to minus k x dx. Integrating on both sides, we will be left with something called v square is equal to minus k by m. What's the integration of this one? X square by 2 plus some constant. V is equal to minus k by m, and we can replace the constant here. While the body is at the last position, as at the displacement, that is a amplitude of the motion, then the velocity should be 0. So in that case, it becomes actually something. When you do that, the equation comes out to be v is equal to omega under root a square minus x square. This is the equation that will come out for the velocity. And from if you differentiate this one, then you will get the the equation for acceleration. So Now, in these equations, it is not exactly in terms of x, right? Although this will is also very useful. Many a times it is directly used and you get the answer. So you have to remember two different types of equations in this chapter. One in terms of displacement, another in terms of time. Both are essential. Although the slide has not given the uh, this sort of equations with respect to the distance covered, but they are equally essential. Coming to the velocity thing, in terms of the this thing with respect to time variable, the equation looks something like this: v is equal to omega a sine omega t plus phi. All right. And now this is the basic definition: x is equal to a cos omega t plus phi. Now if you differentiate this one, हम अगर डिस्प्लेसमेंट का दिया हुआ होता है इक्वेशन विद रिस्पेक्ट टू टाइम, तो हम वेलोसिटी कैसे निकालते हैं? dv by dx by dt is equal to velocity, right? When you do this thing over this one, you will get exactly this thing, the velocity. All right. Now अगर ये हो गया है तो डिस्प्लेसमेंट का हमने समझ लिया और इसका भी. और अगर हमारे पास वेलोसिटी का इक्वेशन है, इफ यू हैव द वेलोसिटी इक्वेशन विद रिस्पेक्ट टू टाइम, इट इज वेरी इजी फॉर us to get the acceleration equation, right? Because dv by dt is equal to acceleration. If you have this thing just differentiated with respect to time, ओमेगा ए ऑलरेडी कांस्टेंट है, बाहर आ जाएगा. साइन का डिफरेंशियल होता है कॉस थीटा. ओमेगा टी का डिफरेंशियल करेंगे तो ओमेगा एक और बाहर आ जाएगा, तो ओमेगा ओमेगा स्क्वायर इनटू दिस थिंग. नाउ एक्सेलरेशन क्या आ गया? एक्सेलरेशन इज इक्वल टू माइनस ओमेगा स्क्वायर ए, आई थिंक ओमेगा स्क्वायर इंटू द सेम थिंग, राइट? सो माइनस ओमेगा स्क्वायर इंटू एक्स आ गया हमारे पास. एक्सेलरेशन इज इक्वल टू माइनस ओमेगा स्क्वायर एक्स. तो यहाँ पर से क्या हमने हमने जहाँ से स्टार्ट किया था ऑलमोस्ट सिमिलर चीज आ गया है, जहाँ पर हमारे पास के का वैल्यू है. सो वी स्टार्टेड विथ एम ए इज इक्वल टू माइनस के एक्स. व्हेन यू कंपेयर दिस एंड दिस, इट इज सिंपली ओमेगा इज इक्वल टू अंडर रूट के बाई एम. ऑलराइट, यही है. So omega is a constant here, which is called angular frequency. There are two things here. एक तो हमारे पास जितना टाइम में कवर किया इसने पूरा एक साइकिल, let's say it started from 0 0 and it went out to the right path and then came back and then covered the rest of the half path and then came back. When it covers a whole cycle, the time that it takes is called time period. Obviously, time period with t sign. How do you define frequency? Frequency is simply 1 by time, always. Now this was with respect to distance, but हमारे पास एक और तरीका है इसको एक्सप्लेन करने का, which is in terms of angle. अगर आप यहाँ से स्टार्ट होकर वापस जब यहाँ पर आ रहे हो, उस पूरे प्रोसेस को अगर हम एंगल्स में डिवाइड कर दें तो होगा क्या? ये 0 है, ये 2 पाई, राइट? तो यहाँ से यहाँ तक क्या हो रहा है? फॉर एग्जाम्पल एक सर्कल है, उसमें बॉडी यहाँ से स्टार्ट किया और वापस यहाँ तक आ गया, तो उसने कितना एंगल कवर किया? थीटा. अगर उसका हम डिफरेंशियल निकाल लें डी थीटा बाई डी टी, मान लो ये बॉडी यहाँ पर है, यहाँ से, तो उसका जो एंगुलर डिस्टेंस है थीटा, अगर उसको डिफरेंशिएट करें विद रिस्पेक्ट टू टाइम, उसका पोजीशन को, एंगुलर पोजीशन को, तो हमें मिल जाएगा ओमेगा, विच इज द एंगुलर फ्रीक्वेंसी और एंगुलर वेलोसिटी. अभी इसमें हाँ, एंगुलर वेलोसिटी क्या हुआ? रेट ऑफ चेंज ऑफ थीटा विद रिस्पेक्ट टू टाइम. बस इतना ही है. अगर ये सब क्लियर है, सो दिस पार्ट मस्ट बी क्लियर. फ्रीक्वेंसी जो हमने अभी डिस्कस किया, द स्मॉलेस्ट इंटरवल ऑफ टाइम आफ्टर विच द मोशन इज रिपीटेड. एक साइकिल में जितना टाइम लगता है, बस वही चीज है. डेफिनेशन ऑफ एस एच एम. नाउ दिस टाइम वेरिंग क्वांटिटी, ऑफ कोर्स अगर ये पार्टिकल यहाँ से यहाँ जा रहा है और ये वापस आ रहा है तो अलग अलग टाइम इंटरवल पे अलग अलग पोजिशन है ना इसका, और इसको हम यहाँ से इस इक्वेशन से फाइंड करते हैं जहां पर इसका फेज एंगल the whole phase angle is equal to omega t plus phi, and phi is where is the initial phase angle. मतलब उसने जब स्टार्ट किया था तब कहाँ से स्टार्ट किया था. इट इज नॉट नेसेसरी कि वो मीन पोजीशन से स्टार्ट करे, राइट? अगर वो कहीं और से स्टार्ट करेगा तो कितना एंगल उसको कवर करना पड़ता अगर वो मीन पोजीशन से स्टार्ट करता, उसके रिस्पेक्ट में अगर हम फाइंड करेंगे तो दैट विल बी फाई एंगल. सो दैट इज दिस वन. नाउ हाँ, इसके बाद हम ये वाला पार्ट डिस्कस करते हैं इन विच अगर आप फर्स्ट ऑफ ऑल हमारे पास क्या क्या इक्वेशन आ गया है. वेलोसिटी का आ गया है, एक्सेलरेशन का आ गया है, डिस्प्लेसमेंट का भी है. अगर हम यहाँ पर से एनर्जी फाइंड करना चाहें तो एनर्जी क्या होगा? फर्स्ट ऑफ ऑल काइनेटिक एनर्जी, दैट इज सिंपली हाफ एम वी स्क्वायर, राइट? So half mv square, when you do that, half into m into, what's the equation of velocity here? Velocity is this one, omega a sine minus omega a sine omega t plus phi the whole square. Then you are left with half into m into omega square a square sine square omega t plus phi, right? So this is the kinetic energy. अभी हम एक और चीज यहां पर है. फॉर एग्जाम्पल एक बॉडी है जो एसएचएम कर रहा है. अभी यहाँ से ये लास्ट इसका फाइनल मैक्सिमम एम्पलीट्यूड है. अभी यहाँ पर अगर पहुंचा है या फिर अगर इसने कवर कर लिया यहाँ पर पहुंचा है वापस, तो इसके पास जो पोजीशन है उसकी वजह से तो वेलोसिटी है ही. ये वापस जा रहा है तो उसके पास तो वेलोसिटी है ही, तो काइनेटिक एनर्जी होगा. बट क्योंकि ये इस पोजीशन पे है तो क्या उसके पास पोटेंशियल एनर्जी भी होगा? पोटेंशियल टू गेन वेलोसिटी फर्दर. अगर ये वापस आकर इसका वेलोसिटी इंक्रीज हो रहा है मीन पोजीशन पे तो उसके पास कुछ तो पोटेंशियल एनर्जी होगा ना, जो एड अप हो रहा है उसके काइनेटिक एनर्जी में ताकि उसका वेलोसिटी इंक्रीज हो जाए. तो दैट पोटेंशियल एनर्जी वी आर टॉकिंग अबाउट, वो कैसे हम फाइंड करेंगे? एक्चुअली वो स्लाइटली लेंदी है. पोटेंशियल एनर्जी इज एक्चुअली इक्वल टू द वर्क डन बाय द फोर्स, वर्क डन बाय फोर्स, एंड द फोर्स इज नथिंग बट माइनस के एक्स एंड डॉट डी एक्स. क्योंकि एफ डी एक्स का इंटीग्रल अगर करेंगे तो हमारे पास पोटेंशियल एनर्जी आएगा, मतलब वर्क डन आएगा, और वही वर्क डन किया जा रहा है उस सिस्टम के जिसकी वजह से उसके पास बाद के थोड़े टाइम में उसके पास पोटेंशियल एनर्जी आ जा रहा है. तो फर्स्ट ऑफ ऑल हम यहाँ पर देखते हैं. अगर ये बॉडी ये मीन पोजीशन है, यहाँ से स्टार्ट किया वापस आ गया, अभी यहाँ पर आ गया तो इसके पास तो कोई भी पोटेंशियल एनर्जी वापस बचा नहीं है. जो भी मैक्सिमम उसका एनर्जी था वो वहीं पर आ गया है. तो इसका मैक्सिमम एनर्जी अगर फाइंड करना चाहें तो कहाँ से आएगा? यहाँ से इस इक्वेशन से आ सकता है. जो भी इसका काइनेटिक एनर्जी होगा मेन पोजीशन पे वही तो उसका मैक्सिमम टोटल एनर्जी हो जाएगा. तो टोटल एनर्जी विल बी इक्वल टू हाफ इंटू एम इंटू ओमेगा स्क्वायर ए स्क्वायर. अभी साइन ऑफ वट एवर एंगल, what is the maximum of sin theta? Maximum sin theta is 1. So 1 square multiply करेंगे तो इतना ही रह जाएगा, and that will be your total energy of the system, which is equal to potential energy plus kinetic energy. When you do अभी हमने यहाँ से actually derivation part लिख दिया है, but that derivation is not exactly required because we have other means as well. So what you do here is potential energy, right? What we want to find out potential energy, so that is total energy minus kinetic energy. What is total energy here? What half into m half into m omega square a square minus half into m omega square a square sine square omega t plus phi. When you take this as constant m omega square a square 1 minus the rest of the thing are the same except 1 minus sine square omega t plus phi. Now we have something which we have already seen 1 minus sine square whatever angle sine square theta that becomes essentially cos square theta, right? So यहाँ पर बन जाएगा हमारा हाफ इंटू एम ओमेगा स्क्वायर ए स्क्वायर cos square theta. This is the potential energy. All right. So these are the three important equations: total energy, kinetic energy, and the potential energy of the system. अभी अगर इस माइंड मैप में नहीं गिवन है, but I think a graph is much more helpful in this case, in which potential energy and energy and versus time, and this is from 0 to t टाइम पीरियड. अब यहाँ पर 0 से स्टार्ट होगा, मान लो मीन पोजीशन से स्टार्ट कर रहे हैं, तो हमारे पास तो कोई भी पोटेंशियल एनर्जी है नहीं, पर हाई काइनेटिक एनर्जी है. तो यहाँ से इट लुक्स समथिंग लाइक दिस. वाइल एंड दिस इज फॉर द काइनेटिक एनर्जी. वाइल यहाँ पर इसका पोटेंशियल एनर्जी कुछ भी नहीं है, तो पोटेंशियल एनर्जी का ग्राफ कुछ ऐसा दिखेगा. This is potential energy and this is kinetic energy. But total energy तो is a constant term. Half into m square omega square m into omega square a square. There is no term of time with it, and it is actually equal to the maximum of either kinetic energy or the potential energy. So the graph for total energy will look something like this. Sorry. Yes, this is total energy. It is always fixed. It does not change. But the components of total energy either gets converted into higher potential energy or higher kinetic energy. All right. But the addition of both of them will remain exactly equal to the total energy always. अभी यहाँ पर हमने एनर्जी का डिस्कशन कर लिया है. So I think this part must be very clear. I think this was what we started with, and there are a couple of things which yes. See, this part is not in syllabus as well as this part. Forced oscillation and damped oscillation are no longer in your either of the syllabus of JEE or NEET. So there is no need to cover this. Anyway, it was a burden for the students earlier. So now coming to pendulum. How do you find out pendulum? First of all, what we are trying to discuss here is, let's say there's this fixed point around which we have a bob, and in the presence of gravity, what we are going to do here is let the pendulum oscillate. So it will come here. This is the mean position, the vertical line from the hinge point, and it will again go back. It will come back. So it will start oscillating, right? Now, this will be oscillation for a large amplitude, means large angle. But while you reduce the angle to a very small angle, when the oscillation is very minute, for example, it is only like this, only very small portion, then this small portion comes out to be almost like a simple harmonic motion. Otherwise, the longer oscillations will not be exactly simple harmonic motion, but the shorter oscillations will be. Why? Because I think it will be much lengthy for me to completely explain, because that will lead to taking the component of gravity, because gravity has a force, and the component of the gravity in this direction will be the reactionary or restoring force, and we already knew that restoring force, see, यहाँ पर I think we can take it up. A is equal to G sin theta, right? Where this is theta. Yes. And now when you do A, we already knew from this thing, theta, can we equate it to be almost equal to sine theta be equal to theta? Why I took negative here is because it is opposite to the direction of the acceleration, right? The theta. Now this looks something like omega square A, omega square, isn't it? So I just told you that how can we approach this problem? The derivation is slightly lengthy. That is why we are not doing it here. But this will exactly be almost equal to a simple harmonic motion in which all the equations can be simply applicable, while the time period can be calculated in this fashion. This is I. Let me just write it here. T is equal to, yes, time period we are talking about, 2 pi under root I over mgl. This is general equation. Let me tell you the general equation as well. Let's say there is this any particular body. We are going to make it perform simple harmonic motion. What we are going to do here is hinge it with the maybe this point, and what we do is, let's say this is the center of mass, and when you hinge it, it will be perfectly vertical because center of mass will tend to come to the exactly vertically lower position. That is fine. Now this is the hinge point, and now you make it oscillate a little bit. So just a whole bunch of mass oscillating like this. All right, it's like your phone oscillating about one point. Now for this thing, what we do is, for the time period, this is the equation where 2 pi is the very simple thing. I, what is I here? This is the moment of inertia. Moment of inertia. Moment of inertia of what? Of the entire body about this axis of rotation. You must have learned in the rotation chapter about the moment of inertia, about a fixed uh, about a fixed axis. So that is what we are talking about. And mgl, m is the mass, g is the gravity, and l is actually the length between center of mass and the hinge point. The shortest distance between the hinge point and the center of mass is l here. In case of this thing, a bob, let's apply this equation. T is equal to 2 pi under root I. What is the, let's say the mass is m and the length is l. Then what is the this thing? What is the moment of inertia going to be for this particular mass about this axis of rotation? Of course, it is a point mass, so it will be mr square. But the length between them is l, so ml square. Ml square divided by mgl. Mgl, m gets cancelled out, one of the l gets cancelled out, and you're left with 2 pi under root l by g. This is the time period for uh, simple harmonic motion for small oscillations of a pendulum. This is a simple pendulum, and this is compound pendulum, meaning any object can be treated as pendulum here. Now if these two are clear, yes, then I think frequency we have already talked about, and that is pretty much it for this part. Yes, a resonance, when frequency of external force is actually equal to natural this is about the forced oscillation. This is about the forced oscillation, you do not need to worry about. So yes, every oscillation is periodic, but not every periodic motion needs to be oscillatory. Means uh, basically the initial part we discussed कि first there can be any motion which is periodic, मतलब ये घूम फिर कर अगर वापस आ जाए तो it will be called periodic because it came back to the original position and the original velocity it started with. That will be periodic. But this type of specific uh, moving around about a fixed position is called oscillatory motion, in which the two halves are actually equal always. And when this there is a specific type of oscillatory motion in which if the force or the restoring force is always equal to or proportional to the distance which it has covered from the mean point, then उस type of motion को कहेंगे हम simple harmonic motion. So I think this the first part is pretty much covered. Now coming to the this part of the mind map, which is more about waves. What are waves actually? First of all, let me just go back and talk about this thing. Let's say there is this particle which is performing SHM in the vertical direction. No problem. But just assume a particle was oscillating in this direction, but it is inside a container which is moving in a horizontal direction. This motion is with respect to the box, but the box is also moving. Then the total velocity or the actual velocity, actual motion of the particle will not be exactly this up and down, but it will be up and down along with moving in the fixed direction with a constant velocity forever. So it will actually be something like this. The moment it starts going up, it also has a velocity here, so it will look something like this. Why? Because uh, if you only consider the velocity in the upward direction, the component of velocity at any point or component of movement of any point in the upward direction, तो हमेशा वो SHM के बराबर ही होगा. This particle is performing SHM, but in addition to the motion of SHM, इसके पास एक और component है velocity का, which is constant in the rightward direction. That is why this is moving something like what we call a wave. ऑलराइट. नाउ एक वेव में फंडामेंटल चीजें कुछ कुछ होती हैं, जैसे कि डिस्टेंस. दिस इज कॉल्ड अ crest. This is called a trough, the deepest point or the lowest most point. The uppermost point is called crest. This is called mean position, and we can draw it in the form of graph as well. Now अभी यहां पर से स्टार्ट किया और इधर ऐसे गया और यहां पर जैसे ही गया, after which do you observe that the motion is exactly a very copy of this motion, and everything after it is a copy of it. So it basically means कि यहाँ पर एक cycle complete हो रहा है, जिसके बाद the same cycle will get repeated over and over again. So basically यहाँ पर जो cycle है, it is exactly the SHM, right? Because SHM में भी ऐसे होकर इधर जब आते थे वापस इसी मेन पोजीशन से, उसके बाद the same motions would resume. It is exactly the same. It's just that यहाँ पर एक velocity, fixed velocity इसको दे दिया गया है. Nothing else has changed. So this is about waves. And of course the time period is the same. Time period is the time which the body or the motion, the wave takes for one cycle. एक साइकिल के बाद स्टार्ट जैसे किया, उसके बाद एक साइकिल जैसे ही लगा, उसके बीच का कितना टाइम हुआ है, दैट विल बी टाइम पीरियड. एंड फ्रीक्वेंसी इज ऑलवेज इक्वल टू 1 बाई टाइम पीरियड. दैट इज फाइन. यहाँ पर भी एक्चुअली ओमेगा का होता है. ओमेगा इज इक्वल टू 2 पाई एफ और 2 पाई बाई टी. सो सिमिलर डेफिनेशंस एज द SHM, बट यहाँ पर एक और चीज़ है, वेवलेंथ. It is basically from distance covered in one cycle, horizontal distance covered in one cycle. That is called wavelength. अब यहाँ पर वेलोसिटी अगर फाइंड करना होगा तो सिंपली लैम्डा बाई टी कर दूंगा ना मैं, क्योंकि एक साइकिल में द हॉरिजॉन्टल वेलोसिटी इट हैज कवर्ड इज एक्चुअली इक्वल टू, और हॉरिजॉन्टल डिस्टेंस इट हैज कवर्ड इज एक्चुअली इक्वल टू वन वेवलेंथ, एंड उसी वन साइकिल में जितना टाइम लगा है वो तो टी है। तो वो एक साइकिल के लिए मेरे को we have both the distance covered and the time taken. So if we do this, we'll get the velocity. Now let's compare it with the SHM as well. The equation for SHM looked very much like y is equal to omega, wait, not omega, it was the definition of velocity, a into cos omega t plus phi. अभी यहाँ पर अगर मुझे ये, दिस इज फॉर SHM नॉट वेव, अभी यहाँ पर मैं क्या करूँगा, अगर मुझे कोई कंपोनेंट ऐड करना है विच इज डिपेंडेंट ऑन द वेलोसिटी, बिकॉज इट आल्सो हैज सम वेलोसिटी, राइट। अगर एक फिक्स टाइम पे देखें तो वी हैव डिफरेंट पोजीशंस एंड डिफरेंट वेलोसिटीज ऑन डिफरेंट वाई फॉर ईच ऑफ देम। हाउ विल यू फिक्स वाई? सो यू विल हैव टू गिव द डिस्प्लेसमेंट एज वेल हियर। इसका मतलब कि यहाँ पर कुछ मॉडिफिकेशन करना होगा, y इज इक्वल टू a cos kx minus omega t plus phi, or we can even write it as maybe some of you may be uncomfortable with it, so I'll write the opposite, omega t minus kx plus phi. Abhi including this kx, where k is a constant here, including this kx actually takes care of the horizontal movement of the particle as well. So अगर यहाँ पर आए, where is that equation for, yes, this is the general equation for this thing. See, plus minus अगर यहाँ पर जो भी रहे, these are all about directions. For example, the general convention is, or the general result is that if both are if both omega t and kx are both in the positive direction, or both in this positive thing, then the wave is going backward. If either of them, either this one or this one, minus omega t plus kx, or kx minus kx plus omega t, either of them is there, then the wave is moving in the right direction. Okay, this can be done with the several maybe experiments. Experiment not exactly experiment. What you do is maybe plot the sine graph after some small time t, and then you will see actually the graph has shifted either in the left direction or the rightward direction. So by doing that you can uh, conclude on the direction of the movement. And with what velocity will the graph move? That will be the this thing velocity. This is the velocity of movement of the wave, not the velocity of movement of particle. Particle velocity is always dependent on this thing. Particle is just moving up and down, right? It is the wave which is traveling in the horizontal direction. So this thing is it is simply, yes. Now velocity is simply this thing. See, it is very much similar to this thing, this equation, right? Or let me just take it up. Y is equal to a cos omega t minus kx plus phi. When you do dy by dx, you will get velocity. Sorry, dy by dt, you will get the velocity. When you do this, a comes out, and the differentiation for cos theta is simply minus sine theta omega t minus kx plus phi. And when you differentiate the what is inside the bracket with respect to time, these will give you 0, while this will give me an omega. So it will actually be a omega sine theta, sine omega t minus kx plus phi. So that is this thing. Velocity is equal to this thing. I think it should be not yes, not a omega square, but a omega simply, minus a omega, and the acceleration will be equal to a omega square. So this was about the equation of the wave, although we have several things to discuss as well here. Now, equations of the wave has been done. Let me just talk a little bit theoretical part, that this thing. There are two types of waves. Let me just talk about it. Let's say this particle is doing SHM in this direction, and then you gave this velocity. Then the particle moves in something like in this fashion. While the wave is moving in this direction, the particle are actually oscillating in up and down as the initial SHM. So in this case, the particle movement is exactly perpendicular to the wave movement, or the direction of the wave movement. In this case, it is called transverse wave, in which the particles move in the direction perpendicular to the overall movement of the wave. Whereas there could be another type of wave जिसको हम कहते हैं longitudinal wave. अभी हम क्या करते हैं, एक SHM हो रहा है इस डायरेक्शन में, उसको हम क्या करेंगे, let's say we give a velocity in this direction, then the particle will look something like this, right? So it is also doing an SHM, while the velocity in the right way direction is always getting added up. So this type of motion or the wave is called longitudinal wave, where the particle oscillates in the same direction as the movement of the wave. All right. So this is about longitudinal wave. An example for longitudinal wave could be sound wave, in which होता क्या है कि एयर के अलग अलग, maybe you can consider them as air blankets. When you give it a sound, then this air blanket comes close to the second one, and after which the second one moves to the right, and it comes to the closer to the third one. So it is actually pressure which is increasing and decreasing, and some sort of movement of the wave. While the overall the sound is moving in this direction, the pressure components of the this oscillation are also moving in either this direction or the opposite, the same direction. So that is why it is called longitudinal wave. And the example of transverse wave could be maybe string wave. String wave means अगर आप काफ़ी लॉन्ग डिस्टेंस पे दो एक स्ट्रिंग को बांध दे और एक एंड पे ऊपर नीचे कर रहे हैं, तो इट विल जनरेट अ वेव इन दैट स्ट्रिंग, इन विच आप क्या कर रहे हो, आपने बस अपना हाथ ऊपर नीचे किया है, बट द वेव इज एक्चुअली ट्रेवलिंग इन दिस डायरेक्शन. So the particle that you have held in your hand, it is moving up and down. Of course, each of the particles in that wave is also moving up and down, but overall the wave is moving in this direction. So this type of motion is called, or wave is called, transverse wave. And the example could be string wave, even light electromagnetic waves could be example of this. So this was about transverse wave and the longitudinal wave. And let me just yes, we can discuss about this one. We have already talked about this in the SHM, so it is exactly the same thing. Angular frequency, wave, time period. Wave number is a different thing, new thing here, that it is inverse of the wavelength. Simply, the definition of wave number is inverse of wavelength. It actually signifies that in a time period, how many number of wavelengths it has covered. So that was transverse wave and longitudinal wave. अभी इसके बाद हम ये छोटा सा पार्ट करते हैं, in which let's say you have a string tied from here, and you want to generate a wave here. Of course you can do that, but with what velocity it will go, or the wave will travel. We have an equation for that. V is equal to under root T by mu, right? So T by mu, I think it is given m here, but it should be mu. Yes, m is generally m is generally defined as mass, where the term in the denominator is actually mass per unit length, not mass. So where T is the tension in the string, and mu is the mass per unit length of the string. It means for 1 meter of the string, what is the mass of the string? That thing, the ratio of mass and length. When you do that, you will get the velocity, horizontal velocity of the wave. And yes, from this thing actually comes this part, which is the longitudinal wave velocity. It is equal to speed, अगर sound का हम calculate करें, v is equal to under root b by rho, or p actually, where b is the bulk modulus. Bulk modulus, you must have learned about, is the one of the fundamental properties with respect to the contraction or the compression of volumetric compression of materials. And this thing, in other forms it can be related to gamma p upon rho. This is the density, this is also density, while this is pressure, and this is the ratio of uh, specific heats, right? Cp by Cv. I think you must have learned about that in your thermodynamics, that the ratio of specific heat at fixed pressure and with respect to the specific heat capacity at fixed volume. That is the basic property of any gas. So that is it, gamma. For air, or for any, I think diatomic particle, it is 7 by 4 5, that is 1.4. So that is the speed of sound. I think we already talked about it. Electromagnetic waves, these are very basic fundamentals, that one of them is mechanical wave, in which a particle propagates or particle moves. In this electromagnetic waves, particles are not there, but it is the intensity of electric field and magnetic field which oscillate with each other. It is just the intensity of the electric field and magnetic field. They are always perpendicular to each other, and they are oscillating. And there is this matter wave, in which all these subatomic particles and all, they can form the waves. So this has been covered. I think this is a pretty basic part. Now coming to this thing, I think few things are left, in which most important is this, of course, this part. I think it has also been removed. Doppler's effect. I think yes, Doppler's effect has been removed. But anyway, I will discuss just in case if you ever come across with it, because it was one of the most important parts of the sound waves and sound. Doppler effect. Let's come to Doppler effect, or maybe superposition first of all. So basically, it talks about that. Let's say this is a wave traveling this direction, and this is another wave. Sorry, in this direction, what will happen when they interact with each other? Means uh, two persons are speaking, and when their voices are interacting with each other, what will happen? What will happen is, if you consider this point and the corresponding point when it will come here is maybe this point, the amplitude of both of them, let's say this is the amplitude, this is the main position, this is the amplitude, and this is the another amplitude. Amplitude is getting added up as it is. It is just the superimposition, the two waves which are getting added up. So the amplitudes, individual amplitudes will also get added up. So this will be the individual amplitude. It will be simply added up. The other equation that is usually talked about is the intensity. What is the intensity going to be? So it will be simply I plus I1 plus I2 plus 2 I1 I2 into cos theta, where cos theta is the difference or the phase difference, this whole thing squared. That is the intensity. I1 I2 cos theta. So phase difference you already know from SHM. The same thing is given here as well, कि आप कहाँ से start कर रहे हो, आपका wave कहाँ से start कर रहा है. If it is starting from here, this point, phi is going to be 0, and if it is starting from somewhere else, then phi is going to be let's say it is starting from here, the wave starting from here, we are monitoring it from a point which is here, then this is pi by 2, right? 90 degree. So that will become initial phase angle. So difference between theta is nothing but phi 1 minus phi 2, difference between two phase angles. So this was about superposition. Both amplitudes are getting added up, while the intensity will get or will interact with each other with respect to this formula. Now I think Doppler effect, we can take it up. So Doppler effect is basically that whenever this particular wave is there, it is traveling in this direction. Now let's say this was the source, it also started to travel in this direction. What will happen is the wave will get compressed. Why? Because as the particle is moving in this direction, more number of waves will get stacked to each other, because the source has moved also, right? The wave which has been generated has been generated, but for the another wave to be created, more lesser space is available, because the source has moved to some direction or to some distance. That is why they will get stacked up, and frequency will get heightened up, increase, right? Because frequency is nothing but the this thing, uh, the number of cycles in 1 second. It is of course getting stacked up, so it will be, the frequency will increase, the time period will decrease. For giving such kind of relations, we have the Doppler effect. This effect is called Doppler's effect. Doppler's effect. You must have came across this one when you are at the railway station maybe, and the train is approaching. When you observe the sound which is for the approaching train, the whole time the quality of sound somewhat changes. It is not exactly the same as the volume increase or volume decrease. The something in the quality also changes, and while the train goes past you, the the change is very drastic, if you have observed it. So that is called Doppler's effect, and the change in frequency is equal to initial frequency multiplied by the velocity of this thing, speed of sound, minus velocity of the object with respect to velocity of the sound minus velocity of the this thing, source. Now the this thing, Whether this one is positive and negative or this one is positive or negative can be determined uh, with respect to the direction of movement of sound. If it is in uh, the velocity of the object or the velocity of the source is in the motion or is towards the propagation of sound, it will be called as positive, and otherwise it will be called as negative. So that is the basic Doppler's effect. Do not get confused in the signs. It is very easy to remember that this one, that whatever direction that you have assigned to the direction of movement of wave, it is always from the source to the observer. The wave will travel from source to observer, otherwise it won't be heard, right? So that is called positive direction. The opposite direction will be called negative direction. So you have to assign v naught and sorry, vo, object velocity, and source velocity accordingly with that sign convention in mind. Now अभी हमारे पास स्टेशनरी वेव, ऑर्गन पाइप, ये छोटा सा आई थिंक इट इज़ मोर टू बी रिमेम्बर्ड. फॉर एग्जाम्पल अभी हम क्या कर रहे हैं, दिस थिंग, स्टेशनरी वेव कैसे क्रिएट होते हैं. फॉर एग्जाम्पल दिस इज अ वेव, this is a wave, and there's another wave which is exactly like this, in which all these points will get added up and the resultant will be actually something like this. It means it is a fixed wave. It does not virtually move with time. It is just expanding and decreasing at its position itself. That is called stationary wave. So in the stationary wave, the fundamental frequency means uh, the first frequency at which it is possible. That is given by this equation. In the organ pipe means there are two different types of organ pipes. One may be closed and another may be open. The sound in this thing is something like this, while in this one the sound waves have to be with the difference of pi by 2, and in this one, a closed organ pipe, the difference could be pi by 4 here, the phase angle difference. So based on that, this is the first or fundamental frequency. This is the first harmonic. So these are the things: first harmonic, fundamental frequency. And in the open pipe, it can only be in the multiples of pi by 2 angle, right? So this thing, that is why the fundamental frequency of first harmonic looks something like this in this case, and for the closed one it is v by 4l. Higher harmonic, both odd and even, yes of course, because it is the first. See, it is taking pi by 4, sorry, lambda by 4, and it is taking 3 lambda by 4. If you look it from the waves perspective, it is taking 3 lambda by 4 distance, while it is taking lambda by 4. So it is always coming in the odd multiples, right? While in this case it is taking up lambda by 2, and when you complete another cycle inside the open pipe, it will be lambda by 4, sorry, lambda, complete lambda, and then it will be 3 by 2 lambda. So it is in the multiple of lambda by 2. That is why it will end up giving this value. In a closed pipe, higher harmonic, odd only, and in the open organ pipe, for example this one, then both odd and even. So I think that was it for this mind map. I think for the SHM, I think you need to visualize more. But for the waves part, it is more of a equation based chapter. That if you remember the formula and a little bit of visualization, if it is there, then you will be able to solve it. So that is all. please keep the formula in mind, and especially for the waves, because the formula for systems can be derived pretty easily, no problem. So that is all for today's mind map. Thank you.